So we're going to do our little introductory video for magnetism. Essentially, this is still just electricity, but it's with moving charges now, and moving charges create this magnetic field. Now, I showed you before that for electric fields, we had the divergence of the electric field, and that was the charge density over epsilon naught. And we had the curl of the electric field was 0, and it was this one, it was this curl being 0 that allowed us to come up with the idea of voltage and all that stuff. Well, when we get into magnetism, we have two similar looking equations. B is the letter used for a magnetic field. It's a vector just like electric field was, similar idea. And then we have a cross for that as well. So we have a divergence. We have a curl for magnetism, except these don't equal same thing. Here, magnetic fields, they have no divergence. They don't diverge. Basically, this is the statement that all field lines that you draw, and you draw the field lines the same way you would with positive and negative charges, but all the field lines, they form closed loops. So all field lines form closed loops. So the only thing you have to change over is none of these, technically, they may not fit on your paper, but none of them go out to infinity. They all form closed loops. So if you stay on and follow one magnetic field line long enough, you'll eventually make a loop back to where you started. Here it does have a curl then, because these things are looping around and bending, and it is the permeability of free space times J, our current density, instead of charge density. That's supposed to be a J. Okay? And so we have that, and that means it does have a curl, which means these things state that there are no monopoles. So what we had with electricity was you could have just a positive charge or just a negative charge by itself, totally isolated. Right, a positive charge or a negative charge, and they could be totally independent of each other. Over here, we don't have positive, negative. What we have are north and south. I'm sure you've heard that before. North end of a magnet, north pole of a magnet, and the south pole of a magnet. They're just arbitrary names. They're just there for no real particular reason. But the norths are kind of like positives, and the souths are kind of like negatives. And the difference is we cannot ever have them isolated. And as we go through this more, you'll understand hopefully why they cannot be isolated, why you can't have just a north magnet or just a south magnet. If you take and split this and you cut this magnet right down the middle, you end up with two smaller north-south magnets. No matter how many times you do it, right down to just even a single electron is a north-south magnet. So you know there's no split in it. Just like with electrical charges, opposites attract, like the north attracts to the south, but likes repel. North repels north, south repels south. And we can draw these field lines just very similar to how we drew the electric field lines. They go, except instead of being out of positive and into negative, they're out of north and into south. Okay, so they'll look like that, and so it'll look very similar, something like this. All right, out of north into south, and then some going to be too big to draw. You know, it gets weaker as you go further out. Those eventually would loop back around. You know, they go way around or something, and some might go way off of here and come back in. But they eventually would come back in, go back in there. So out of north into south. And if we look real close, it's going to be kind of hard for me to draw it. I didn't think ahead. But these field lines, if you follow them and you actually went through the magnet, they go through the magnet and form closed loops with those field lines. That these magnetic fields actually go through the inside of the magnet. Like I said, they form a closed loop. If you follow one long enough, even if there was one that like went way off over here, you'd eventually follow it and follow it and follow it, and it would, oops. I'm trying to follow it way too far down there. You'd follow it and it would eventually come back up and loop back up on itself. Okay, it would eventually do that. But this is very similar to the field we got around a positive and negative charge next to each other. If you think about Earth, Earth is itself has a magnetic field to it. It's like a giant magnet. Um, and if you think about it, if you're holding a compass, compasses like to, they attract, like a north attracts to a north. So if I put a compass here, or I'm sorry, the north repels from a north, it's going to point that way. And if I put it over here, it's going to point this way. They basically point along anywhere you put a magnet. It's going to, oops, I drew the arrow the wrong way that time. Anywhere you put a magnet, it's going to point and line up tangent to that field or parallel to that field, tangent to the curve, wherever you put it. And the reason is, like, say if I put one here, the north end, the arrow end of my compass is going to repel away from the north end here, and the south end is going to attract. So if you're on Earth, right, this is Earth, let's say, and you're holding a magnet or a compass, and the north end of that magnet points toward the North Pole, right, the North Pole here, and the north end of this magnet is pointing towards it, that should tell you that this is not actually the North Pole. That's the South Pole. So what we have to do is realize that this is actually called the geographic North Pole, like up there at the top, right? The geographic North Pole is actually the magnetic South Pole. So if we looked at Earth as pretty much how it acts, as though it's a giant bar magnet, what you have is a big bar magnet like this, where this is the South Pole and this is the North Pole. Okay, and then this is the geographic south, magnetic south, geographic north is magnetic south. And the field lines will extend out like this around, just like in a bar magnet. It's a little different than the bar magnet because going out of north, so they're going this way, because we have solar flares and we have the magnetic field from like the sun and everything affecting it. All right, I messed this line up right there. We have the magnetic field from the sun affecting it. So what it actually does is this kind of gets warped towards one side, where this side gets like pushed out further, where the sun would be over here. Here, you know, the sun, solar rays, and magnetism come here, and they kind of warp this. So it's not exactly like a magnetic field. It's more like it kind of ran out of room. It's like we have the nice magnetic field kind of squished on this side, and then it's like stretched out long over on this side away from the sun because it has that effect on it. I kind of drew over the equations there, but that's okay. All right, so just kind of remember that geographic north is magnetic south. Okay, so how do we calculate a force from this field? Because ultimately we did electric field just to get force, and that was pretty easy to calculate. It's a little different here. The actual relation for this that you come up with is the force of a magnetic field is equal to Q V, which is in this case is not voltage but the actual speed of the particle or the velocity of the particle, cross product to the magnetic field. Okay, so this is the cross product of two vectors, and it gives you a third pseudo vector. It's like another vector. It's a little different. For everything you need to know at this purpose, it's exactly a vector, but later on you'll learn it has a little bit of a difference between it and other vectors, so it's called a pseudo vector technically. But this is just like we talked about before whenever I brought this cross product thing. It just means that we're going to multiply together the perpendicular components. So it's QV perpendicular to the magnetic field. All right, that's the way I like to remember it, is that V has to be perpendicular to a magnetic field, and the way you'll get it in your data booklet is F equals Q V B sine theta, where theta is the angle between V and B. Okay, that's the way you're going to get it. This is the way I like to think of it. So if you have a magnetic field, now because this is a cross product give you a third vector that's perpendicular to both the original vectors. We have to worry about a way to actually draw this because we're going to have to draw three-dimensional vector pictures. So we'd have to have vector, if V and B are both, you know, like say if V is pointed up and B is pointed right, that means that something perpendicular to that is either into or out of the screen here, or into or out of the page that you're working on. So we have to be able to come do that. So what we're going to do is we're going to draw X's for, this is a vector pointed in, and then we're going to draw dots. So it's kind of like the tail feathers of an arrow going away from you, and we're going to draw dots for a vector pointed out. Okay, we're going to do that, and that'll help us to be able to draw our more 3D type pictures. Okay, so keeping that in mind, what we can do is say, let's have a vector field here, magnetic field. This is pointed into the screen, so a uniform magnetic field in just this region pointed into the screen, and we're going to say that this magnetic field cuts off right along this dotted line, and this is our B field right there. It's a vector. So what's going to happen if we send like a proton, a little positive charge? We're going to send it into this field at velocity v. And so what this does is there is only a magnetic force if the velocity of the particle is perpendicular to the magnetic field. So if you had, for example, if I draw this over here, if I have a magnetic field pointed this way, right? If I have a magnetic field like that and I send a particle parallel or anti-parallel to it, where its direction is that way, there's going to be no force. It's going to be no force. There's reasons for this. It gets kind of complicated. You have to combine both electrostatics and special relativity, but you ultimately get an answer for this, and I may discuss that with you later, especially when we get to when we do special relativity way later. But at the moment, you just need to think of this as this is only a force if a velocity is moving perpendicular to this, and then the force is also perpendicular to the velocity. And if we get a force perpendicular velocity, think back to our centripetal motion. What's going to happen? Our particle here is going to enter the magnetic field, and it's going to get turned. The force is going to be perpendicular to that direction, so this is velocity, this is force, and it's going to turn. And it's going to keep turning because up here, now the velocity is this way, and the force is still perpendicular to it. So essentially, magnetic fields only supply centripetal forces. They don't supply any other kind of thing, and then this would come back out of the field. If the field region entered there, it would just turn it around. So essentially, magnetic fields, or magnetic fields, they only supply a centripetal force. So magnetic fields do no work. And if you ever come across a situation where you think a magnet is doing work, it's technically not the magnet doing work, it is the induced electric field that's doing work. Because we're not talking about changing magnetic fields here, we're only talking about static ones, so there's no work done. But if you get in a situation where you have a changing magnetic field, that changing magnetic field creates an electric field, and then the electric field can do the work. But the magnetic fields, they don't do work. So if you, like, say I took a you think you have a magnet doing work, like I hold a magnet over some paper clips and the paper clips jump up to it. It's not the magnetic field making them jump up, it's the electric field that gets induced by you moving that magnet to that location that then creates the force that pulls them up. So only changing magnetic fields can do work, but they don't really do work. It's the induced electric field that does work. So you've got to remember this. Magnetic fields do no work. Okay? They can only turn particles. They can only apply that centripetal force. And so force is perpendicular to any little displacement that occurs, which means work would be zero, because work is force times parallel displacement. Okay? So that's basically the idea here. It only causes charges to move. So now, how do you know what direction it's going to turn it? And what you have to have is what's called a right-hand rule. And this will be our first one. This will be our number one right-hand rule. And the way this works is, I'm going to just describe it to you, but basically you point your fingers in the direction of the velocity. So fingers in direction of the velocity. Your palm, you point in direction of the B field, and then if you hold your thumb out, like hold your thumb out extended, like you're hitchhiking or something, then you get the thumb points out, thumb is in the direction, it tells you the direction of the force. Okay, and I know that doesn't make a lot of sense, so I got a little picture here to look at for it. I found, and let's look at this picture here. What you can see is fingers pointed in the direction of the velocity of the particle. Your palm, then you turn until it's in the direction of the magnetic field. If you hold your thumb out to the side, then you've got the direction of the force. And this works, and there are other versions of this right hand rule where you point along the B field and your fingers point along F and your thumb points out V, and there's all different kinds of versions of this. You really only need to know one. I don't care which one you know. I think there's a different one in your book, but it doesn't matter. All that matters is you can use at least this one or use the one in your book. I think this is the easiest one. Fingers in the direction of V, palm in the direction of B, F is pointed out by your thumb, and then you know the direction of the force. And the reason this works is because your fingers are perpendicular to your thumb and your fingers are both perpendicular to like a vector that would be perpendicular to your palm, like whatever direction your palm was facing. They're all perpendicular to each other, and so that would work. And this is called the right hand rule. If you do it with your left hand, it's not going to work. And what this does is it points out the direction of F on positive charges. For negative charges, it is giving you the negative direction of F. So it's giving you negative F. You'd have to then flip it around to do the direction of force on a negative charge. Don't forget that. That's very important because you'll accidentally tell that the negative charge is going the wrong way. And so this will curve around and come back out and curve a certain amount. If you look at this, if you pointed your fingers, you can do this. You point your fingers in direction of V, point your palm toward the screen because my magnetic field is going into the screen, and then your thumb should be pointed up. And you can do that all the way along here, and you see your your thumb always ends up pointing toward the center. This is also a way that we can use to tell a lot of different things about particles. For example, if I send two particles in that have the same charge but different mass, right? I send them in at the same speed, well then the one with the greater mass is going to turn more slowly, and then I could work out, I could even separate them. I could say, oh, I can tell here that I've got this particle because I can see how big of a curve it went around and I know its mass, so it must be this particle. If you send a particle in and it goes straight through, then you know it has to be neutral and have no charge to it at all, because if there's no charge, this is 0. And if you send a charge in and it curves the other way, then you know it's going to be a negative charge. So I could send two particles in, one curves up, one curves down. I know that one is positive charge, one is negative charged. If they curve the same amount and they were going the same speed, then I know they have the same mass. So maybe I have an electron and an anti-electron, or a proton and an anti-proton, two identical particles with the same mass. If they're going the same speed and they have the same charge and they curve different amounts, then I can tell which one is more massive. The more massive one is going to turn more slowly and make a bigger circle than the sharper turning, less massive one whose inertia is less. Okay? I think that's pretty much it for what did I want to do in this first video, kind of get you introduced to it, give you our first little equation for it, and we'll go on to some more complicated versions of moving charges, like actually creating the magnetic fields. Here, all we did was talk about what happens to moving particles in a magnetic field. Now we want to actually talk about how do we create these magnetic fields, and we'll start that in the next video. All right, that's all.